try this again. This is our additional discussion on the calculations involved in Chapter 11. Okay, just a couple of key terms. Solution composed of a solute, that's the thing that was dissolved, and a solvent, that's the thing that's doing the dissolving. And while we think of solutions most often as being two liquids together or liquids and solids, as you can see from this table, we actually can have multiple types of phases combined to make what we consider a solution. And a solution, remember, is a homogeneous mixture, and it is mixed at the molecular or atomic level. Okay, concentration. This is how we measure how much solute we have relative to either the amount of solvent or the amount of solution. And we have multiple units that we use to express this. And so this discussion is going to focus on, basically, if we have one type of unit of concentration but we need a different one, how do we convert between those two? Okay, the different types of concentrations, I'm just going to kind of go very quickly through this because you can read the definitions and all in your text, but the focus of this is going to be the calculations. Okay, so molarity you should be familiar with. It has a little bit of that in Chapter 11, but if you need a review, remember it's back in Chapter 4. Then we have percent by mass, which is just like any percent. It's going to be grams of solute per total grams times 100. Percent by volume, same thing. It's going to be volume of solute per total volume times 100. Parts per million, grams of solute per grams of solution times 10 to the 6th. And then similarly, parts per billion, same thing except times 10 to the 9th, trillion, etc. Okay, and we use these again. You see these most commonly when you're talking about water quality, air quality, things like that, where you have really, really, really low concentrations that you're dealing with. Okay, molality. This is a new one. Moles of solute per kilograms of solvent. So up to now, we've been in the denominator dealing mainly with the whole solution. But for this one, it's just the grams of the solvent, or kilograms of solvent. Okay, and that's a good point there that they make, that molarity, one thing to be aware of, molality will not vary with temperature because we have moles and mass in there. However, because molarity is moles per liter and volume is affected by temperature, so molarity, just be aware that molarity can change with changes in temperature. Mole fraction, I think we talked about mole fraction back when we were doing gases, and the definition is still the same. It's moles of the component divided by total moles. All right, and then mole percent would just be mole fraction times 100. All right, so like I said, I was going to go through those pretty quickly because you can pause me on the vodcast, but let's look at some problems here. All right, here we have hydrogen peroxide is 30% by mass and has a density of 1.1 grams per cubic centimeter. All right, so the thing that I like to do on this is break the units into pieces. All right, these are defining ratios, and whatever conversions we make, those ratios have to hold true. All right, and so you'll kind of see how that really drives the way that you solve these calcs. But I find it really helpful to just sort of break the units apart and remind yourself what it is that you have. So 30% H2O2 by mass. Okay, and this we're going to assume this is an aqueous. Since hydrogen peroxide is soluble in water, we'll assume that the other component of the solution, the solvent, is water. All right, so this says I have, whoops, let me get the pen going. Maybe. Okay, so this says that I have 30 grams of H2O2 per 100 grams of solution. Okay, so this is kind of what I mean by breaking the units apart. And then it says it has a density that 1.1 grams of H2O2 is, no, I'm sorry, that's my bad. That's not, that's the solution density. Let me erase that. It's not letting me erase. Why not? Here we go. Okay. Let's go back. That is the solution density. So that says 1.11 grams of solution is equal to, and let's cubic centimeters and milliliters, so we'll say 1 milliliter of solution. Okay? And we want to know, so that's what we're given. What we want to know is we want molarity. So we want moles of H2O2 per liters of solution. Okay? So again, like we were doing before when we were dealing with ways of calculating molar mass, you want to just treat the two pieces of the unit you want separately. So look at how can I get moles of H2O2. Well, here I can use the 30 grams of H2O2 per 100 grams of solution. So if I have that many grams in 100 grams of solution, that means if I take 30 grams of that, and we'll use approximate, so that's going to be about 34 grams in 1 mole of H2O2. And so that gives me 30 divided by 34. So that gives me 0.882, that's moles of H2O2. So I have 0.822 moles of H2O2, and I can put that in my denominator. And then, alright, I can use that 0.882 as long as whatever I put in the denominator is equivalent to 100 grams of solution. Does that make sense? 30 grams of H2O2 per 100 grams of solution. So now I've converted it to moles, 0.882 moles of H2O2, but that goes with the 100 grams of solution. So I don't need grams of solution, I need liters of solution. Well, I got my solution density that I can use there. So if I have 100 grams of solution, I can use that density, which tells me that for every 1.11 grams of solution, I get 1 milliliter. All right, I need it in liters, so 1,000 milliliters to 1 liter. So 100 divided by 1.11 divided by 1,000. So that gives me 0.09 liters. 0.09 liters. And so 0.882 divided by 0.09, and that says I have a molarity of 9.8. Okay? Alright, let's look at another one. Okay, here we have, it's bringing in actually a volume percent and to molarity. Okay, so same kind of approach. It's given us, here we have the density, but these densities are of the components. Okay, if it doesn't specify, if it gives you a density and it doesn't specify that it's a density of a specific component, then it typically means the density of the solution. So like what we did before where it's giving you grams of solution, or grams of solute per grams of, or milliliter, sorry. Grams of solution per milliliter of solution. All right, but here we're actually looking at the specifics. So let's see how we're going to use those. So again, I want molarity. So my molarity is going to be of the ethanol. So I want moles of the ethanol, which is ethanol, C2H5OH, okay, over, again, liters of my solution. So let's see what we have. If it's 95%, 92 proof, and it says that proof is twice the volume percent. So 92 proof is going to equal 92 divided by 2 is going to equal 46%, and that's a volume percent of the ethanol. Okay, so what does that mean? That means that if I have 46 milliliters of the ethanol per 100 milliliters of my solution. Okay? Alright, so let's just attack the numerator. We need moles of ethanol. Alright, and the only ratio that we have is this volume percent. That's the ratio that whatever concentration unit we convert it to, that relationship has to be maintained. So I can use the 46 milliliters of ethanol as long as I attach that to 100 milliliters of solution, which that's going to be easy because in the denominator, actually let's do that first, right? We know we're going to use 100 milliliters of solution is how many liters? 0.1 liters of solution. Okay, so now 46 milliliters of ethanol, 2H5OH, and then the ethanol density says we have 1 milliliter is 0.8 grams of the ethanol, and I need moles, so molar mass is going to be 46 grams in 1 mole. So that's going to give me 40, oh, wow, never mind, 0.80 moles. This problem looks like it must have come off an AP test. It's one that you can do without a calculator, actually. Okay, and so there we have what we need, and we get that it's going to be 8 molar on there. Okay. So that one was easier than it actually looked. Okay, next one. We want molality of ethanol in a water solution that is prepared when we mix 50 mils of the ethanol with 100 mils of water. Okay, and it gives us a density. So we know that we have 50 milliliters of the ethanol per 100 milliliters of water, and we're wanting molality, which is a little m, and that is going to be moles of ethanol per kilograms of the solvent, which in this case is water. Okay, so let's look at the top. If I have 50 milliliters of ethanol, I can use the density to get that into grams. So I have 1 milliliter is 0.789 grams, and that's 46 grams in 1 mole of the ethanol. So that is 50 times 0.789 divided by 46. So 0.858 moles. Alright, so that's going to be moles of the ethanol. And then we have 100 milliliters of water. That's our solvent. The density of water, we'll use that 1 milliliter is 1 gram. And then 1,000 grams is 1 kilogram, because we need it in kilograms. So we have, that gives us 0.1 kilograms to go up there. And so my molality then is going to be 8.58. Okay. Alright, here we have a density and the amount that it contains of the solute, and we want the molarity. So molarity, we're going to have moles of the magnesium nitrate per liter of solution. And it's telling me that the solution density, so 1.114 grams of solution is equal to 1 milliliter of solution. Okay, and we know that also that the solution contains 96.6 grams magnesium nitrate per 1 liter of solution. Okay, so we want moles. Why in the world do we need... Okay, we're going to take this one a step further because this problem is... I'm not even sure why this one's here because it's way too easy, right? Because what do we have to do? We don't even need the density, right, on this one because we can just actually just do a factor label with the grams per liter. So magnesium nitrate is, let's see, 24, and I've got 2 nitrogens, it's 28, 3 times, so 148 grams of magnesium nitrate in 1 mole. I think this problem must have been a part of a multiple part problem. Okay, 296.6 divided by 148. So about 2 moles of magnesium nitrate in 1 liter per 1 liter of solution. So there, with just that one conversion, there is our molarity. Okay. So that's that. But now, what if the question were, find the molality? Okay, so let's take a look at that, because we do have enough information to find our molality also. Okay, molality is going to be moles of magnesium nitrate per kilograms, and this is, if that's a salt, so it's going to be an aqueous solution, so kilograms of water. Okay, so let's see, a couple ways we can do this. Alright, we already know our moles. We have 2 moles in a liter of solution. Okay, so let's go ahead and we're going to put our 2 moles on there. So as long as the kilograms of water that I use on the bottom is the same number of kilograms of water that are present in 1 liter of solution, then I'm good to go. But that's what I want to do. I have to maintain that ratio there. So what do I know? Well, I know that 1 liter of in 1 liter of solution, what do I have? Well, I know that I have 296.6 grams of my magnesium nitrate, and then I have some grams of water. That's what I'm trying to find. But what other piece of information do I have? I had this density up here, and that tells me that it's this many grams of solution in a milliliter of solution. Well, if that means if I have a liter or 1,000 milliliters, I'm going to have 1,114 grams of solution. So that's the mass of a liter of solution. Well, I know that 296.6 grams of that is the magnesium nitrate, which means the rest of it must be water. So I just take my total grams, because this is the mag nitrate, and part of that is the water. Alright, so if I take the grams of the solution minus the 296.6, and that's going to give me what? Oh, let's not divide. Let's subtract. 1114 minus 296.6. Okay, that gives me 817.4 grams of water, which is, I'm going to put up there in units of kilograms, so that would be 0.8174 kilograms. So 2 divided by 0.8174. So the molality is going to be 2.45 little m for molality. So that would be just taking that problem a step further on there. So you can do, and that's a typical thing that you end up doing with molality when you're converting to molality. The key thing is to remember what is, in the grams of solution you have, it's grams of solute plus grams of solvent. Alright, one more. We want the mass percent of copper sulfate in a solution that has a density of 1.3 grams per milliliter. So 1.03 grams of solution in 1 milliliter of solution. Again, we'll just remind ourselves that is water and copper sulfate that makes up that mass there. And it says I have 1.22 moles copper sulfate in 1 liter of solution. That's my molarity. And I want a mass percent. So what I'm trying to find, I want grams of copper sulfate per grams of solution times 100. Okay, so this one's not too bad. We have 1.22 moles of copper sulfate. I need that into grams. So 1 mole of copper sulfate is going to be 56 plus 32, and I'm getting about 152 grams. Whoops, is that right? Yeah, 4 grams copper sulfate. Okay, so there's my numerator. No, don't do that. Oh, no. Okay, slight detour. Okay. Where was I? Oh, okay. And then grams of solution. Well, if I use the 1.22 moles to get the grams, I have to use 1 liter to get my grams of solution. So we're going to use, if I have 1 liter or 1,000 milliliters of solution, and this tells me that 1 milliliter is 1.30 grams of solution. So that's going to be 1,300 grams of solution, and then times 100, 185.44. So that gives me 14.3%.